Alright guys, you're welcome to our next tutorial on the Python programming series. Today we shall continue with the trees data structure in Python, which is very important. Very important in a lot of applications, and you see that in most coding problems a lot. So it's good that we spend some time to actually dig deep and understand how we can write Python codes that represent trees. Now today we are looking at binary tree. So we know that a tree has one intrinsic structure, that at every node the maximum of children you can have is 2, meaning that a node can have 0 children, 1 child, or 2 children at the most. So we will use binary tree to build a binary search tree implementation. And what's the thing about the binary search tree? It's just a special kind of tree that has a unique structure. And the structure is that every child on the left, every left child must have must be less than the parent, and every right child must be greater than the parent. Or another way is every child of a node, every left child of a node must be less than the node, and every right child on the node must be greater than the node. And how do you know which one is left and which one is right? Just you facing the screen, whatever is on your left is the left, whatever is on your own right hand is the right hand, is the right. So for instance, 3 is the left here and 7 is the right here, because it's on your left hand and 7 is on your right hand. So what do you do when you have a number that is equal to a child that is equal to the parent? Well, in our own implementation we just ignore it. We don't want any duplicate in our tree. But most times you just put it on the left with a child that is less. Okay, so this is a binary search tree that you see here. Alright, so let's now go into how we implement some of the operations. First of all is we need to write a class for a tree, and the class for a tree is written this way. You see, if you're like me, most times when I do a coding problem on trees or binary search tree, I get stuck easily because you have a lot of recursion taking place, an infinite amount of loops taking place. So, and that's part of the motivation for this tutorial series, to be able to help people like myself that get stuck when writing codes for search trees, for binary trees and the like. So first, this is a very important concept that I also realized I haven't missed, is that to be able to write your code for any tree, you need to think in this fashion. First, you need to think of tree as an object, and you also need to think of the nodes as an object. Without that thinking, you will just go veer off the wrong track. So first of all, you have to think that a tree consists of different nodes. Or I also think of it. That is enough. A tree consists of different nodes. So you write a class for a tree, Then you also write a class for a node. Then the class for the tree will be the high level class that your users can interact with. The class for the node will encapsulate all the data about each of your node. So you wrap your data, for instance, the value of the node or the name of the node, what its children are, the left child and the right child, what they are. It will be wrapped inside the class called node. So to build a simple class, you just declare the class as tree and you don't supply it any argument. As you can see here, there are no parameters for defining a tree, but every tree should have a root node, which intrinsically you just declare it as none. So this is a tree, but this tree has its node to be none. It looks very, can be kind of difficult to understand, because sometimes when I write a code for a tree, I want to put a comma here and put data and initialize the self.root node to be something. Then I get confused down the road. I don't know, maybe that's the same experience for you, but I find it very easy to grasp. Just declare a class for your tree and initialize its root node to none. So you have a tree and you imagine it this way: the tree has a root, because every tree should have a root. Without a root, there is no tree. But in this case, the root is initialized to none. So that tree has intrinsically a root that is yet to grow, kind of. Okay. So in class 3, we now want to start implementing some of the operations for the object that will be instantiated from this class. Now, before we do that, because we're going to implement essentially two operations, which is insert and remove, to insert a node and remove node, we look at a subtask, which is how you can find the minimum and maximum node in a tree. One important thing you should know that before you can find the minimum and maximum nodes in a tree, that means the values that are stored in each node must be comparable, sort of. If you are not able to compare the values on each node, or let me just say, if you are not able to compare each node, then there's no way you can know which is the minimum or maximum. So if it is in your own code, you have to find a way of implementing the sorting, the ordering. So let's say you want to find a minimum in a binary search tree. Having the understanding that a binary search tree maintains a peculiar kind of structure, that everything on the left of a node is less than or equals to it, and everything on the right is greater than it. So to find the minimum, you just go downwards to the left, and to find the maximum, you just go downward to the right. Simple. So let's say a code that implement that. So now it's getting more interesting now. So this is a code that implement to find minimum. First, let's abstract away all this one. Assume all these are not there. So you find a minimum. What do you want to return? You must return something. A node. Good. Alright. So let's abstract away this. So to find a minimum, if it is a tree, then you expect it to have a root node, even if it is none. So you need this variable called current. This is where the magic of programming now comes in, where you start introducing variables and you begin to have a understanding of how many variables you should introduce and what each variable should do to be able to help in the programming construct. That takes a lot of practice and a lot of seeing experience, seeing examples and explanation like this to be able to come up with that. And that's one of the challenges that I also face when writing program. Trying to know when to introduce a variable, trying to know what the variable should do, and trying to know how many variables to introduce. Those three questions are very important to successfully write programs to solve problems. And also, in addition, how the variables should be manipulated or updated. Very important. Even in dynamic programming, so very important. And it takes a lot of experience or practice in seeing examples and working problems to be able to grasp it. So we bring up a variable called current, and you initialize that current to be equals to the root node, whatever the value of the root node is in that tree. Don't let us forget that we have just initialized our tree, which we soon see again here, and it has an attribute called root node. Okay, so we see it again in code. So once you have initialized that, assume the highlighted is not there, so you can just return that current, and that gives an answer provided that tree does not have any child, or since you're finding minimum, provided that tree does not have any left child. If the tree in question does not have any left child, then we don't need what is highlighted. Just get the current and return the current. So return the root node. So current is equal to the root node, and return that current. That's all. Because you might need some of this intuition when you begin to try to optimize your code. If you have a code like this, if I give you a tree and say this is the way the tree is, and I begin to do this like this and on like this, and it goes on like this, and everything is just so long, and I ask you to find the minimum. Don't bother yourself traversing all this side, since you know that this is a binary search tree. It's a binary search tree, and I say you should find the minimum, and you're trying to go this way. No, you're not going to get the minimum. Once you know that these trees satisfy the binary search tree implementation, just return the root. Because it doesn't have any left child, then it cannot have anything that is lesser than the left child anymore. You want to take a moment to pause to think about it. So if I'm to write a code for this, I don't need this highlighted code. I don't need that. I only just need to get the current node and return that current. and that makes my program very efficient. Very efficient. Just that. So now, if I now begin to now have the knowledge that I have left child in my binary search tree, then for me to be able to return the minimum node, which in this case is this, I have to traverse from the root and go down until I get to the minimum. But I don't know. Remember, we're digging deep to be able to understand how to write programs. Because when you see the program, yeah, it's easy to grasp. But when I close this and I say write a program, something similar like this, not exactly this, then you might begin to find it difficult to write. Because you really did not understand the logic behind the binary search tree. But once you understand the logic behind it, you can figure out the program for just anything about binary search tree. So, for you to be able to return this node, which in this case is the minimum, you have to start from the root node, because you only just have reference to the root node. You have to continue to traverse down until you get to this. Now, one naive programmer will want to say, okay, I start with the current. I say current dot left, and I say put that one into another variable, and I say that one dot next. I put it into another variable, and I say that one. Then how many variables are you going to create forever? Because you don't even know where this ends. So that will not be a good approach. So the best way to now do that is for you to be able to check that your current dot left child exists. So now, let me pick another color. Oh, sorry. So now this is where we are. We're on this node. So you are now here in this program. You now say current dot left child. Why it is not none. That is, if there is a current dot left child. So here, this is where you are. What is the left child of this? This one. Does it exist? If it exists, then you have to update your current. Your new current becomes this. That is what is being done inside this while loop. Make the new current to now be this. Then you come back again to the while loop, and it checks. This is now your new current. Does this new current dot left child, what is this new current node dot left child? This one. Is it none? Then you check. Is this none? No. Okay. If it is not none, update the current to now be this. So this becomes your current. You get the gist. Then it comes again. Does this one, which is now the current, does its left child, this is its left child, is it none? Oh, it's not none, there's something there. Okay, update your current now to this. So this becomes your current. That's what's been done here. Then again, you come in here. Does this one, which is current, we are now here, current dot left child. This is what it says. This is saying this line of code, why current dot left child is checking. Does this current, this is your current name, does its left child exist? That's another way of saying it. Is it none? Oh, it's none. Okay, don't update. What do you now do? Return that current. This is the current. Repeat that again. Does this current, no, this is your current, no. Does it left child exist? That is it none? So what is the left child of this? Oh, there's no left child. It is none. So at that time, this while loop becomes false. So don't update. Just return the current. It is the minimum. Takes some time to be able to think through. It took me some time too. So that's that. Now let's now go into the insert operation. In the insert operation, to insert a node, you now begin to see how we manipulate the uh, variables, and I will do that in the next series. Thank you for listening. Do let us know what your comment has. See you in the next one. Thank you.